to speak here. So it's really a pleasure to be at ACT in general. And also, I mean, this feels even more special because of Paul's celebration. Benedict already mentioned how much Paul has done for the community, but I think many of us also know that he has done a lot for us individually. So I was not only his PhD student, but I mean, he's also the one who introduced me when I was still an undergraduate student to Logic and Automata. And yeah, Paul was obviously an incredible PhD advisor too. So I don't think I would be, I mean, I would probably be doing something much less interesting if I hadn't met him. So yeah, it's nice to be here. All right, so I'm going to talk about HyperLTL and HyperCTL star. So these are temporal logics for hyperproperties. So let me begin by explaining what hyperproperties are. So yeah, so the idea is that we want to specify behaviors which relates different executions of the system. So imagine you have a system with different kinds of users. So some have high security clearance and others have low security clearance. So you have a system with some private and public inputs and outputs, and essentially you don't want anyone who has only access to the public data to be able to deduce anything about the private data. So to express this, you will need to say, for instance, okay, so if I have two executions where the public inputs are the same, for instance, maybe I want the public inputs, outputs to be the same as well, and not depend on the private inputs. So this needs to relate different executions. So a classical example is non-interference. There are many variations of that. So maybe you want two different executions with the same public data to have the same public outputs. Maybe you want to relax that a bit. So say you have a system where you can input passwords. So maybe obviously you don't want to disclose the passwords of your users, but maybe you want to disclose whether the password was correct or not. So this would be declassification. So you have many properties like that. And the point is that, I mean, in the verification community, we love to use LTL and CTL star and temporal logics like that. But with these logics, you can only talk about one execution at a time. And here we want to relate multiple executions. So there have been several extensions of classical temporal logics to that. One of them is HyperLTL, where you take LTL and you add quantifications over executions. Another one is HyperCTL star, where you have both branching behaviors and quantifications over executions. So let me go a bit more in detail into the syntax. So let's start with HyperLTL. So in HyperLTL, essentially what you have is you have a LTL formula like that. And in front of the formula, you may have a bunch of quantifiers. So here, pi ranges over different executions of the system. So I will also say trace. So here, when I say trace, it's not Markowitz trace, but just a word. And so, yeah, so you have these quantifiers. And then instead of saying, okay, A is true at the current position, you need to say which trace you are looking at. Okay, so you can say A pi to say that's proposition A is true at the current position on trace pi. Okay, so let's see just an example. Okay, so for instance, you may want to say, okay, for every execution pi and pi prime, if everywhere the public input is the same on pi and pi prime, then the public output is the same everywhere as well on pi and pi prime. Okay, and when we have this globally, essentially we move synchronously both in pi and pi prime. Yeah, so and the point is we just have so this LTL formula and then all the quantifiers are in front. So a model of HyperLTL formula is then, so for LTL, a model would be a trace. Here, a model is a set of traces. So a set of words over some atomic proposition AP. And you can also say that the transition system satisfies the formula if the set of traces of the transition system satisfies the formula. Okay, so let's look at one more example. So if you have this simple transition system where, okay, you start here, you can do A, and then at some point you loop. Never mind. So we have all these traces, and we can see that this formula, for instance, is satisfied. So what does it say? It says, okay, whatever pi I choose among all this execution, I can find a pi prime where at every position, the A's are shifted between pi and pi prime by 1, okay? And we move synchronously in the trace. So the G means we look at vertically at every position and we check that we have that. So please feel free to interrupt me at any time if you have any questions. So the syntax of HyperCTL star is essentially the same, except here we allow quantifiers to be within the scope of some temporal operators. So we just can have them everywhere instead of just in front. But the main difference is in the semantics. So instead of evaluating the formula on a set of traces, you look at the execution tree of some transition system. So model of a formula will really be a transition system and not just traces. But otherwise, yeah, we still have the synchronous executions between all paths in the computation tree. And yeah, essentially when we have a new quantifier in the middle of the formula, we look at the latest path we have quantified over, and then we can branch. So yeah, this generalizes both HyperLTL and CTL star. So let's look at just one example to give you an idea of what more you can say in HyperCTL star that you couldn't say before. So for instance, here what we say is, okay, so for every path pi, at every position where I have an A, whatever other path I take from there, the B's are the same on pi and pi prime. Okay, so whenever I have an A, all paths starting from there coincide on B. So obviously you can't say that in HyperLTL because you have no way to know that this path doesn't start from the same state as those two. And you couldn't say that in CTL star either, because in CTL star, I mean, you can branch, you can say for a path, there exists a path, but then as soon as you quantify over this path in CTL star, you forget the first one. You look only at one path at a time. So this is really much more expressive. So the good news about HyperLTL and HyperCTL star is that model checking is decidable. So depending on your preference, it might not be great because it's non-elementary, but it's still decidable. And essentially, the complexity depends on the number of quantifier alternation you have in the formula. So you have a tower of exponential depending on the number of alternation. And I mean, an interesting point is that we have lower bounds both if you fix the formula or if you fix the transition system. So yes, it's high, but I mean, in the example we just had one quantifier alternation, for instance, and often that would be enough. All right. So since model checking is decidable, you can also decide, for instance, okay, is there a transition system with at most k states that satisfy the formula, because you can just enumerate all transition systems with k states and see if the formula is true or not. On the other hand, if you want to know if there is any transition system or for LTL, any set of traces that satisfy the formula, then this is not decidable. Okay. And okay, so that's where we are. So HyperLTL and HyperCTL star have decidable model checking, but undecidable satisfiability problem. And what we wanted to do was to understand exactly how undecidable these logic are. And the answer is, well, very undecidable. So let me start by just a reminder or an introduction to the different degrees of undecidability you can have. So essentially, just as you have many hierarchies for decidable complexity classes, you have also a hierarchy of undecidable classes of problems. So here you have the arithmetical hierarchy and analytical hierarchy are defined in terms of arithmetic. So essentially in this class, sigma ji, the upper index say how many, say in which order of, so we're talking about higher order arithmetic, and the J here says which order of arithmetic we have. So for instance, when you have 0, it's just first order, 1 is second order, and so on. And then the other index says how many quantifier alternations you have in the formula. Okay, so for instance, sigma 1, 0 which corresponds to the recursively enumerable problems. Pi 1, 0 is the dual every time, so it's just co-recursively enumerable and so on. So what was known about HyperLTL and HyperCTL star is, so I mean, in the first undecidability proof, so for HyperLTL, the proof was by a reduction from post-response problem. So it shows that it's at least sigma 0, 1 hard. And for HyperCTL star, it was proven a bit more carefully that it's even sigma 1, 1 hard. And what we showed is that it's actually one level higher than that. Okay, so HyperLTL satisfiability is sigma 1, 1 complete, and HyperCTL star satisfiability is sigma 1, 2 complete. Okay, so here we have essentially existential second order arithmetic, and here existential third order arithmetic. Okay, so it's quite high in the hierarchy, of course. So in particular, what this means is that we can't hope to have semi-decision algorithms. So for instance, there are tools which implements for HyperCTL or HyperLTL semi-decision algorithm when you look only at models of the specific shape. But you can't have or hope to have tools like that for the general case, right? So okay, and the main reason why this is so high in the hierarchy and why there is such a gap between the two is essentially the size of minimal models for HyperLTL and HyperCTL star. So let's look a bit into that. So for HyperLTL, it was already known for some time that, I mean, there is, every satisfiable HyperLTL formula has a countable model, so where you need only countably many traces. And there are examples where you do need countably many traces, that meaning that finitely many are not enough. I mean, the proof is quite standard. So you take any model and then you say, okay, I start from some trace. And let's say I have a formula that exists. So for all pi that exists pi prime, it means that if I take I have Scholen functions, which if I take a trace for pi, we give me a trace for pi prime. So I start from any trace in the model and just I saturate with this Scholen function. So and we reach fixed points and we have a countable model in the end. On the other hand, there are HyperLTL formulas where you do need an infinite number of traces. And this, I mean, I will use this example again after, so I will just give an example. So we can define a formula where the model is exactly, or contains at least, all those traces. Okay, so essentially you have a diagonal of A's on the traces and then nothing everywhere else. So to ensure that you have this diagonal of A's, you can say, okay, so there is a trace where I have A at the beginning. And then you can say, okay, I have A only once. So this is the first formula. For trace, I have not A until then I have A and then not A again. And then whenever I have, whenever I have A here, I can find another trace where A is just after. So that's the last formula. So when I have A on pi, I can find pi prime where I have A at the next position. Right, so that's the kind of things you can easily write in HyperLTL. So for HyperCTL star, this question of how big do you need the models to be hasn't been studied yet. And what we proved is that if we have a satisfiable HyperCTL formula, we can find a transition system where you need only at once the continuum many states. And yeah, there is a formula where you do need uncountably many states. So this is state. So let me explain first why we need uncountably many states, which is, so with HyperLTL, countably many states suffice. Here, it does not. So, okay, we want to ensure that we have, let's say, for every sequence of zeros and ones, we want to ensure that we have a distinct path in our model like this. Okay, so the right path, if we can ensure that we have the right path, then we have here all these successors, we already have exactly 2 to the n many successors. Okay, so to do that, well, we look, we do that in 2 steps. So first we construct the left part, okay? And then we will do the right part. So, okay, so first we can say, okay, we have a model which is split into parts where we have the black states, the red states, and we have zeros and ones everywhere. Okay, then we can say here that we have a full binary tree. I think if I'm on the left part, I always have a 0 successor and a 1 successor. Okay, so then we have already all parts labeled by 0 and 1s. And now, I mean, this is still countable, of course. So we need to make them disjoint. So what we say is that for every black path, we have a red copy of this path. And then we need to check. So this is this formula. I mean, yeah, the details don't matter really. And what you can say then is that, okay, whenever I have 2 paths in that part, well, if I start from the same states, then the 0, 1 labeling will be the same. So I can have copies in this part, but I still need to have at least 1 distinct path for every possible sequence of 0 and 1s. So this means that we will have uncountably many states in that part. Okay? So C many states versus the cardinal of the reals. And conversely, we can kind of apply the same technique as for LTL to show that this is enough. So I don't want to get too technical, but the idea is essentially the same. So we have some Skolem function which take a path and adds new ones. And the point is that when you saturate, it doesn't work the same as for LTL because let's say at the first step, you had this path, then you had this one and so on. After omega step, you will have added this path on the left. And you haven't applied the Skolem function to this path yet. So you can't stop after omega step. You need to go beyond. But yeah, we do reach a fixed point as soon as we get beyond countable. So we still have matching upper bound. Okay, so for HyperCTL star, we have models at most of the size of the reals, and we do need to have that many states sometimes. Okay, so what's the, so I claimed that this was central in the question of the complexity of satisfiability. So the reason why is that, well, if you have, okay, so let's go back to the definition first. So I said that HyperLTL was a sigma 1, 1 complete. So what this means, again, is that you have a formula where you have a first order arithmetic formula, and then you have some second order quantifiers in front. So if you know that you have a countable model, then you can represent a model of a satisfiable HyperLTL formula simply by a function from, okay, so you take, you say which trace you are on, and then which position on the trace you are on, and then you associate some labeling. Okay, so you just have a function from n to n, essentially. Okay, and this is a second order object. So you can say there exists a model by using these quantifiers, and then you can use the first order parts to say it is a model, indeed. Okay, so for the hardness parts, well, the good news is for sigma 1,1, there are still a bunch of nice canonical sigma 1,1 complete problems. And we can, for instance, reduce a tiling problem. So the tiling problem in question is, okay, is there a tiling of the n times n square such that some tiles repeats infinitely often on the bottom? So essentially, we will encode that in HyperLTL by saying, okay, so for each tile, I have a proposition. Each row in the tiling is represented by a trace. And then, okay, so you have a bunch of traces. Now you need to have this vertical order. And for that, we will use a special proposition like that. Okay, so let's say you have this tiling. And so here, each row is a trace. And we add this Y proposition to say on which vertically where we are placed, all right? And then, so we just have a bunch of local things to check. Okay, so, I mean, this is standard encoding, right? So we just say, so for every position, we have exactly one tile. Then Y is true exactly once. This is the same formula as before. And okay, then you need to check the vertical positions. So you say, okay, so if I have a pi, I check the pi prime where the Y is. No, that's not that yet. But okay, so horizontally, you just check, okay, for all trace, for every position, this one and the next one must match. And vertically, you say for every trace, if I find a trace where Y is right after, the tiles match. So this is fairly standard on encoding. And then the specific problem we reduce is to have some tile repeated infinity often, which you can say standardly in LTL. Okay, so then we have that. We have both the upper and lower bound. So HyperLTL satisfiability is sigma 1,1 complete. And now we can come back to HyperCTL star. So it's sigma. So sigma 1,1 is existential second order arithmetic. So a first order arithmetic formula with a bunch of existential second order quantifier. HyperCTL star is a whole level higher. So you have a bunch of third order quantifiers and then the second order formula. And I mean, the idea is just that, well, if you have an uncountable model, then you cannot encode it with a function from n to n more, and you need to go one level higher. So yeah, essentially what is a model? A countable transition system. It's just, okay, the set of states is 2 to the n. Transitions are a subset of 2 to the n times 2 to the n. And then you have the labeling function, which says which atomic propositions are true where, which is just a function, again, from 2 to the n to n. So we just have this third order object. So we say there exists a model by saying there exists a function like this and set of transitions like this. And then we check that it's a model by using the main part of the formula. So the lower bound is slightly less nice than for HyperLTL because, I mean, we haven't found any nice canonical sigma 1,2 complete problem. So we, again, go back to the definition. So we take some arithmetic formula, and so a third order existential arithmetic formula, and we want to construct a HyperCTL star formula that is satisfiable if and only if the first one is true. Okay, and the idea is that so you take your arithmetic formula, and then you replace every quantifier over integers by quantifier over paths. And you just say, okay, so you have a path with, say, zeros and ones, and the one indicates what the natural number should be. And if you have a subset of natural numbers, so second order quantifiers, then you will just say, okay, same thing, I have a path, and the ones indicates which natural numbers are in the set or not. So then you still need to deal with the third order path here. And the idea is that we are reducing different problems, right? We want to reduce truth of a formula to satisfiability. And satisfiability is itself an existential quantifier, right? So the existential third order will just be is there a model? All right, so okay, so we have seen that HyperLTL satisfiability sigma 1 complete, HyperCTL star satisfiability is sigma 1 2 complete. But I explained that this is linked to the size of models. And maybe you may want to argue that, okay, maybe I don't care about infinite transition systems with uncountable branching and so on. Maybe I'm happy to just look at smaller models. So, well, if you want to regain decidability, then you need to restrict a lot. So essentially, you need to, so you have two directions, right? If you have a set of traces, you have an infinite number of positions vertically and horizontally, and you need to bound some direction if you want to regain decidability. So if you look, is there a set of traces with at most k trace such that the formula is true, then this is decidable. If you bound the other direction, so instead of vertically bound, you have a horizontal bound in a way, you say, okay, I look only at traces of length at most k. And because we have infinite traces, okay, maybe we have some ultimately periodic trace where both the period is bounded and the first part is bounded. Okay, so if you bound one of these directions, then it's decidable. On the other hand, if you just restrict to, if instead of bounded you say finite, then this is not sufficient. So in particular, if you ask, is there a finite set of traces that's a set of formula, it's undecidable, but it is recursively enumerable. Okay, you can just enumerate. This is because of the first part. And on the other hand, if we ask the horizontal direction to be finite, so if we ask to have ultimately periodic traces, but with no bounds on how the length can be, then it's the same complexity as the general problem. Okay, so yeah, it's just as hard as general satisfiability. For HyperCTL star, so again, if you want to ask, is there a transition system with at most k states, then you can just check all of them. So this is decidable. If you ask for a finite state transition system, then it's recursively enumerable, but it's still undecidable. And okay, so that's for finite transition system. Maybe you want to have an infinite transition system, but let's say you don't want to have infinite branching, so you want only, or okay, maybe even you want to have a countable number of states. So in that case, it's slightly lower than the general case, but it's still highly undecidable. So it's equivalent to evaluating a second order arithmetic formula. So it's not in any of the sigma ij classes, but yeah, it's just below in a way. All right, so in conclusion, so HyperLTL satisfiability and HyperCTL star satisfiability are both highly undecidable, but HyperCTL star satisfiability is in a way infinitely more difficult than HyperLTL satisfiability. So another way to look at this is that, I mean, this is negative in a way, right? But another way to look at it is that this means that we have a very high computational power in these logics. So when you start to restrict the set of possible models, you don't get a much lower complexity. And yeah, another result that I didn't mention is that, okay, so I mentioned that the model checking complexity depends on the number of quantifier alternation you have. So maybe if you have a formula, you may want to find an equivalent formula with a lower number of quantifier alternation. So unfortunately, this is not possible. And it's exactly as hard as unsatisfiability. So it's by 1-1 complete. So I think that's all I wanted to say. So thank you.
Long live India and France friendship.